Hello everyone, we are Team B5 of MLR Institute of Technology 2022 to 2026 batch. We are here to present our project Adversarial Vulnerability Detection System. This project was completed under the guidance of Dr. K. Shivakrishna, Associate Professor, CSE AML, MLR Institute of Technology. AI and ML have been widely incorporated across various fields, and they have been providing a great deal of convenience for everyone. And this integration is ranging from educational fields to applied sciences like military and medical applications. Application of AI and ML models across these sensitive fields requires a great deal of caution. It while deploying such models across critical fields, one needs to ensure that the models are compliant with relevant regulations and are also robust against various threats that the model might face in a real-world scenario. Adversarial vulnerability system is a TensorFlow-based framework for evaluating vulnerabilities in convolutional neural networks. This is especially against adversarial attacks, attacks that are mostly unnoticed and ignored by everyone. This is a Python-based tool that integrates all the steps of testing a model against adversarial attacks. These attacks include FGSM, PGD, CW, Deepfool, and JSMA. These attacks help one test the robustness of the model across the spectrum. These tests were done across various datasets such as CLFIR10, ImageNet, and MNIST. Our objectives in this project were to design and implement a simulation framework capable of generating and applying different adversarial attacks to cybersecurity AI models. This was completed successfully. The second objective was to evaluate the robustness of commonly used AI/ML models. We had used ResNets and successfully demonstrated and evaluated the robustness of ResNet 15, 18, 108, and 150. The third objective is to analyze and identify the factors impacting model resilience. This was done by comparing various factors such as model type, dataset, and various attacks implemented. The fourth is to recommend practical guidelines for developing robust and secured AI-powered cybersecurity systems. We had achieved this by creating reports that specify the weakness of every model against all the possible attacks that were implemented. These are some papers that we surveyed in order to give our project all the strength it needs. Some of the existing systems are Adversarial Robustness Toolbox, Clever Hands and Foolbox, Robust Bench, and Robic. The problem with most of these is that either they are complex to set up or are not modular enough for benchmarking against multiple models at scale. Even if they do combine both of these, there is a risk that most of them are outdated and are hard to calibrate to modern day needs and modern day attacks. Our proposed system, Adversarial Vulnerability Detection System, or combats all of these disadvantages as it is a modular framework designed to systematically evaluate the robustness of CNN models. Unlike the regular and existing systems in which the user needs to implement the code and set up everything from the collection of the dataset to the evaluation pipeline, our framework takes the brunt of the work. The user only needs to provide the dataset and the model that he is willing to test. The provided dataset can also be used if the user does not have a dataset that is particularly suitable. Since, uh, since it is modular and the framework is relatively complete, the evaluation is comprehensive And since it is modular, you can attack or add or remove additional adversarial attacks as and when needed. The insights are also visualized and as we provide various types of visualization methods such as pie charts, bar charts, tables, and all of this data can be exported in multiple formats. These formats include CSV, JSON, PDF, and Markdown. We also help bridge theory and practice as any new attack that has been recently uncovered in academia can be directly implemented and added to the framework that we have proposed. We had used CIFAR10, ImageNet, and MNIST datasets as these are the most comprehensive datasets that are used in day-to-day evaluations. CIFAR10 consists of 60,000 images. ImageNet is a database that contains multiple images of multiple classes. MNIST is a handset of handwritten digits. All of these combine data across the spectrum, classified and structured data that is based on higher resolution images, handwritten images that are full of variables, and this provides a comprehensive evaluation that is reliable and trustworthy. The hardware requirements for this framework are a bit high, as this is a sorry as all adversarial attacks and the hardware requirements for this project are a bit high, as all AM models and CNNs require solid hardware to run. A high-performing GPU along with an Intel i5 or i7 CPU is recommended. As for memory requirements, we suggest a 32 GB RAM or even a 16 GB RAM would be fine. However, the processing would be a bit slow. As for software requirements, Python and all the listed modules are needed. However, if you use the executable version that is provided, do not need to concern yourself with the software requirements. These software requirements are for those who wish to compile their code from the GitHub libraries. This is the system architecture that we are presenting. The user provides input of dataset and pre-trained CNNs. The dataset is passed to the preprocessing layer where the preprocessing engine works. It resizes the images, normalizes them, and passes the preprocessed images to adversarial generator. Then the clean images are used to create a baseline for predictions. Then adversarial attacks are carried out on the CNN models and the metrics are used to do the degradation analysis. Then we create a matrix of robustness based on per attack and per class. All the vulnerabilities are then tagged and stored in the database. The data stored in the database is used to create reports that are present in the user's dashboard. This is the architecture for various attacks that are being implemented. The methodology of the project is as follows. First, images and CNN models are passed as input. Then, the images are pre-processed and passed on to adversarial generator. Adversarial attack generator generates adversarial images which are used to test the adversarial robustness of CNN models. This is done in the detection layer. Afterwards, the results are stored and reports are generated. Afterwards, it's iterative evaluation from the side of the user. These are the implementation pics of the project. This is the config file that is generated from the data given in frontend, and this is the code for FGSM attacks. This is the login screen, and this is the image that is generated. This on the left hand side is the clean image, and the right hand side are the adversarial images that were generated based on the clean image. As can be seen, it is hard to identify any change in these images from the naked eye. However, models have been giving consistently wrong answers on these images. One can see the dashboard in such manner. You can get an average of accuracy on both the clean and adversarial attacks. You can also see the evaluation history of a particular user. This is how data is stored across the backend. This is the individual graphs for each attack. You can see the attacks attack graphs for PGD and FGSM. This is the overall graph consisting of all the attacks that are currently implemented on the model. As can be seen, one can see the adversarial accuracy, clean accuracy, and the attack success rates. These are the feature spaces of various images scattered across the feature space. The blue is the clean and the orange is the adversarial. As can be seen, despite the differences, one might not notice in any change by the naked eye. And the rest are images that one can see. In conclusion, adversarial vulnerability detection system is an integrated and modular framework for evaluating robustness of deep learning models against adversarial attacks. This is the patent and this is the conference paper that we have published. Thank you.